opportunity to talk in the seminar. And so everything I'm talking about today is joint work with Adam Chapman and Mathieu Florence. And the preprint is on the archive. Okay. So pretty much everything I'll do is going to be working with a field, and we're going to have characteristic P, which is positive prime. And I'm going to be talking about p-algebras. So by that, I just mean a central simple algebra of degree some power of P with center my field at characteristic P. And then also be talking about like P symbol algebras. And so by that, I just mean A, B, and F. Then we can define the symbol A comma B, which is lopsided because we're working over a field of characteristic P. And so this is the algebra generated by the powers of X and Y, so that the X's give me the Art and Schreier extension, and the Y is the purely inseparable subfield, and they anti-commute by the Galois action. Okay. So then I'll also talk about cyclic algebras. So by that, we can just say that it's split by maximal cyclic subfield. Of the algebra. Okay, and then we'll talk, I'll have in there a little bit like a PM symbol algebra. And so by that, I'm going to use a Witt vector of length M over F. And if I take a element of the ground field or the center, then I'll write that as omega comma beta. So this is our cyclic algebra with maximal subfield associated to our Witt vector omega. So giving us our cyclic extension there. So the general questions that we talk about or think about in this paper are as follows. So, I mean, maybe the first question would be, you know, what's the relationship between the existence of a simple, purely inseparable splitting field and the existence of a separable splitting field? So that's pretty well known, that's historic, and I'll go over that. But so as you can tell from the title here, we're really gonna insert the word common so that instead of thinking just about one algebra or one symbol and asking those kind of questions, we'll think about a collection of symbols and think about what happens in that case. Like, so as if there's a common, simple, purely separable splitting field, does that mean there's a common separable splitting field amongst a collection of algebras? So we also here talk about symbol length. Okay, so can we get our hands on some symbol length bounds? And then finally, I would say our last thing is what, if anything, translates to the higher cohomology groups. So Hn plus 1, P to the M, F. Okay, so those are Kato-Milne cohomology groups. So It's basically the outline of what I'm going to talk about. So I guess I'll start with some background theorems. There's a lag with my technology. Sorry about that. Please let me know if it ever goes all the way out. So let's go over some of the background theorems. There's some great classic ones that we get to talk about. So, maybe it's worth starting with the much loved McKinnie-Suslin theorem, which says that the M torsion in Brauer F is generated by cyclic algebras of degree M. Given that M is prime to the characteristic of F, and F contains the mth roots of 1. Okay, and I stole this next term from the Gilles Zamweli book, but an ancestor, I guess they say, and I liked that term. So an ancestor to the McKinnie-Suslin theorem, we can attribute to Albert and Teichmuller. And this is done in the 1930s. Says that basically the McKinnie, though it's backwards to say it this way, the McKinnie-Suslin theorem holds and much easier for p-algebras. So here, if we take F to be our field of characteristic P, then the McKinnie-Suslin theorem holds. So in other words, the P to the E torsion in Brauer F, this is generated by cyclic algebras of degree P to the E. So even more is true and nicely true about p-algebras. And so for that, I would call this, or I like to call this Albert's cyclicity theorem. Which says, in fact, that every p-algebra is Brauer equivalent to a cyclic algebra. So up to Brauer equivalence, everything in sight is cyclic. So it's really nice situation to work in. And it's probably worth noting that these theorems here, both of them, they don't hold on the level of isomorphisms. So like in 1978, I think was the Amitzer-Saltman paper where they constructed non-cyclic p-algebras, and those were generic abelian cross products. And then for the for this McKinnie-Suslin type theorem that says everything is generated by cyclics, you could look at examples like of Karpenko, or those are the earliest ones that I know, where you have indecomposable p-algebras of exponent as small as you want and index as large as you want. There are other examples out there also. But those, so we're really just talking here about Brauer equivalence. Okay, so the key to proving Albert's cyclicity theorem is, like the title of the talk, it's understanding the connection between the purely inseparable splitting fields and the separable splitting fields, or cyclic, I guess I could say there. Maybe I should say cyclic. Okay, and so this is the theorem of Albert. So, which tells us the connection there. So we have a p-algebra A, so over this field F is cyclic, and that's going to happen if and only if there's a B in F star and a P to the R, that's at most the degree of A, so that adjoining the P to the Rth root of B, this will split A. Okay, so for example, the non-cyclic p-algebras by Amundsen and Saltman, they just show that there are no p-power central elements, and so that's going to show that the algebra is not cyclic. Okay. Right, so we understand the connection here with our p-algebras, and so theorem, it'll follow from this theorem that says that we understand that you're cyclic if and only if you have this correct degree purely inseparable splitting field. And the next proposition, so Albert's cyclicity theorem follows from this plus this proposition, which allows you to take two symbols and combine them. Oh, actually, I need to say that it follows from the Teichmuller and Albert result and the following proposition. That'll be more correct. So let's take cyclic A1 and A2 of degree P to the R1 and P to the R2. Oh, I am not having.
Can't see your writing.
Yeah, yeah.
Oh yeah, now we
there
can.
it goes. Ah. Then there exists an R that's at most R1 plus R2 and a B in F star, so that F adjoin the P to the Rth root of B will split both A1 and A2. Okay, so yeah, so from this we see how to prove Albert's cyclicity theorem, because we have that you can write any p-algebra as a sum of cyclics, and then by the proposition, so we know that the algebra in general is cyclic if you can find the right degree purely inseparable splitting field, and by this proposition, for any two, you can combine them and show that they're cyclic, and then you just repeat over and over again. So we get Albert's cyclicity result in that way. That's the strategy for that. Okay, so with a very small alteration of the theorem, mostly just using induction, you can't quite use induction to just say that this applies to any number of common splitting fields. You just have to do a very slight alteration, but you can show that this holds true for any number of algebras. So if we have M cyclic p-algebras of degree P to the Ri, then there exists a B and F star such that F adjoin the p to the rth root of b. This is going to split each ai. And here we have R is at most the sum of the Ri's. Okay, so that gives us a common purely inseparable splitting field for each of those algebras. And the reason that we wanted that change is to prove the following corollary.
So why can't you do this by induction?
Well, because what's going to happen is you'll split A1 and A2. And then, so what would you do there? Then you would take the tensor product of A1 and A2 and let's see, so, sorry, I screwed that up. So you have, so if you just have two algebras, then it's Albert's theorem. And then if you have three, what would you do? You would have a cyclic that splits both A1 and A2. And so that just means that A1 tensor A2 is cyclic, and then you have A3. So then you would have a cyclic that splits A1 tensor A2 and A3, but not each of them individually. Right? Because Albert only applies to two of them.
Okay, thank you.
So the corollary is about the higher cohomology groups. So every class in Hn+1, p to the m of f, this is a single symbol. In Hn+1, p to the tf for a large enough t. Okay, so this is just like the Brauer group situation that says that if you let your cyclic extension be as big as you want, then all the algebras are cyclic or they're a single symbol. So this is a generalization of Albert's result that way. So I'll just say a few words about what these higher cohomology groups are. So Hn+1, p to the m. So these are the Kato-Milne cohomology groups. Okay, so the definition's easiest to define when you just look at the elements of order P. And so this we can write as the co-kernel of the n differential forms by the P map to n differential forms mod the D of omega n-1. All right, so here the omegas, these are the Kähler n forms. So this would be written, you could A or F dA1 through dAn, where the F and the AIs are in F. And the P map, this takes an element of the form. Let me put it down here. So the P map of something that looks like F dA by A wedge dAn by dAn by AN. This does this F to the P minus F dA1 by A1. These are our logarithmic differentials here. dAn by AN. So this has a nice connection with algebras. So of course, if n+1 is 2, then my forms look like, so we're looking at H2P of F. And so my forms, they're going to be classes of things that look like F dA by A. And then this is going to be isomorphic to P torsion and Brauer. And this element goes to the symbol F, comma A. So P. Okay, and so the higher torsion, so we understand H2, and we have a pretty good handle on Hn plus 1 sub P. So if you want the higher torsion, you have to look at the bit vectors. So if you look at Hn plus 1 sub P to the M, so to speak, elements of order P to the M, this is going to be our bit vectors, and we tensor with n copies of F star. And then we take that and we mod out by all the relations that we want so that we get P to the M torsion in the Brauer group, right? We can write these down as follows. So it's going to be, I have my P power, the bit vector, and then tensor anything. So it's a group generated by these guys. I want, the right kind of algebras to be trivial. So I need to kill elements that look like that. And then we have our anti-commutativity property, just like in the differential forms. So you would also kill elements that look like this, where bi equals bj, sum I, not j. Okay. So what the corollary says is that, so we have Hn plus 1 P to the M, F, and it says if we let T be big enough, so we have this natural way to include the P to the M torsion and the P to the T torsion, just like in the Brauer group. This would be for M less than or equal to T. And so that's just by putting the bit vectors into each other the right way. Slowing down, I already wrote that. I didn't anticipate this. There it is, look at that. Okay, so it's saying that, no matter what element you take on the left-hand side here, and we would represent that by some sum of symbols. Right, when we put that in to a high enough torsion group, we're going to get a single symbol. Okay, and the reason that it was really helpful to understand this the right way for algebras is that the goal to get a single symbol here would be to manipulate this class through AT, if these are all symbol algebras of degree P to the M over F, where F here, I need this to be an infinite field. I think that's not a problem. Then we can assume that they have a common purely inseparable field. So we have a beta in F so that the P to the mth root of beta will split each of these guys. Then we can take RIs, and these are in F, and the only restriction here is that they are all FP independent, or linearly independent. Okay, so those are free choice there, but what we then have is that there exists a bit vector of length m, so that the omega, ai, this is given by omega comma, of course I have to change my beta a little bit, but it's beta minus Ri to the m plus t minus I. Okay, and this is our p to the m symbol, f. And this is for all I between 1 and t, and then our A0, we just have our anchor point is omega beta. Okay. So a couple of remarks. So in the proof, maybe I'll just say like very shortly about the proof. You know, we're starting from a nice position here. We're starting where we have this common beta, so that the p to the mth root splits the algebra that's already of degree p to the m. So, you know, our starting point here would have our cyclic algebra given by some bit vector comma beta, right? And what we want to do is we want to, you know, manipulate this algebra without changing it, you know, using symbol manipulation so that the wi's, they all transform to a single omega. And of course the betas, they're going to have to change because I'm not starting with all of the same algebras. Yeah, so you do that one element of the Witt vector at a time. I think that's the whole theme of this whole paper. One at a time. Yeah, and so you do it by proving that you can solve certain equations that let you manipulate the symbol in the right way. That's all I'm going to say about the proof, but that's what happens. A couple other remarks. So this generalizes theorem of Adam from 15 that is just looking at two p symbols. So for every alpha, beta, and f, gamma, I'll just say alpha, beta, and gamma. So if you look at the algebras alpha, gamma, and beta, gamma, so these are just p symbols. So these guys share a purely inseparable splitting field. These also share a cyclic subfield of degree p. Okay, and it's probably worth remarking that the opposite implication fails. So in other words, I can, there exist symbols where you have something like omega, comma, x, p to the m, and omega, comma, y, p to the m. So these guys share a cyclic splitting field, but do not share a common purely inseparable splitting field, degree p to the m. So you can't go the other direction. Okay. So far I've mostly talked about the our common splitting fields and you know, making everything cyclic. So I think about that as, you know, turning many symbols into one. But we could also talk about the other direction, and that gets back to our notion of symbol length. So, you know, how many symbols do you need to express an algebra? Okay, so there's a lot of great backstory theorems on this also. So let's just try to be clear here. So the symbol length of A, if that's in the p to the e torsion of Brauer F. This is going to be the minimum number of cyclics so that A can be expressed as a tensor product of those cyclic algebras. So Ci here is the degree, oops, sorry. Cyclic degree p to the e. These are cyclic algebras over F. And so the symbol length of A here, this is the minimum number of cyclics needed here. Okay, so there's some, like I said, there's some really great theorems. I'll just mention a couple of them. So Florence in 14 proved, so if you have A, so this is going to be a central simple algebra over F characteristic P, and it has exponent P to the E and index P to the N, then you can express A as the tensor product of at most P to the N minus 1 cyclics. So in other words, I'm saying the symbol length of A is at most P to the N minus 1, or the index of the algebra minus 1. And there's some other symbol length results. There's like an original one by Teichmuller. When I did the literature search, I also saw ones by Makaryev and then Makaryev-Lamon. Another one that I'll mention because I'll use it shortly is one that Adam and I looked at last, probably 2 years ago at this point. But we found the symbol length using the P rank of the field. So if F is a field of characteristic P,
It looks like the exponent doesn't play a role here.
the exponent is determining the degree of the cyclics. But you mean in this result here?
Yeah.
Yeah. Isn't that awesome? Yeah. Okay. So we're going to take F to be our field of characteristic P, and I want the finite P rank R. So the P rank, so this means just that the dimension of F over the P powers of F, that's going to be P to the R. Okay, then the symbol length of A, I'll tell you what A is in a second, is going to be at most R choose N, where A, this is going to be an element of H n plus 1 P to the M of F. Okay, so we'll use that to get some bounds below. The other theorem that is a great theorem that we use is from Tignol. So he's looking at the same question that I mentioned. Well, maybe I didn't quite mention it, but all right, you'll see what he does. I'll say more in a second. So yes, F here is field characteristic P, and then so he's looking at for any symbol A. So I'm going to write it in my notation for the omega B. So this would be P to the T. So this is in P to the T torsion of Brauer F. So any symbol that actually has smaller exponents than P to the T, so you didn't kind of fit that in as nicely as possible, you like let the torsion grow. So that has exponents P to the M. And here M, of course, is at most t, we have that the symbol length of A. And then here, I'm going to be specific. I'm talking about p to the m torsion in F, but this can be bounded by p to the t minus m. Okay, so it says, right, we know all of our algebras are cyclic, so somewhere up high in the torsion, it's a single symbol, okay? But if it actually has exponents p to the m, if you want to write it as a tensor product of symbols in the p to the m torsion, you have a bound on the number of symbols you'll need, and that's this p to the t minus m. So that's a really great theorem. If you look at the actual paper, you'll say this does not have anything to do with characteristic P, but everything goes through in characteristic P from his argument. Okay, so what can we say? We can get some results in a few situations, and so that's basically, it's the situations where we understand in the higher Cholmology groups when something is actually trivial. So the first place that we can make some progress here is when n plus 1 equals 3. I mean, we kind of understand what goes on in the Brauer group already, but when n plus 1 is 3, we can look at a symbol A. So this is p to the m torsion in F, and if this guy has exponent p to the m minus 1, then its symbol length in H3 p to the m minus 1 of F is at most, so m plus 1 plus p squared, choose 2. Okay, and I like this proof, so I'm going to say a few words about it. I like the different aspects of things that it brings together. So when you look at the single symbol A in H3, we say A would be represented by a symbol that looks something like omega tensor beta tensor gamma. So this is in H3. It's, you know, should probably put a class around here, but I won't. And omega is our Witt vector, so let's write it as omega 1 through omega m. Then what we see is that the exponent of A being p to the m minus 1, this implies that this algebra, or sorry, not algebra, this Cholmology class, omega 1 tensor beta tensor gamma, that this guy is 0. And that is, this is just a field element, so this is living in H3 PF. And so H3 is one place where we understand when things are 0. So we have Gilles' reduced norm condition says that gamma, this is going to be a reduced norm. So I'll write it as the reduced norm of Z, where Z is an element of this algebra, omega 1 beta. Okay, so that's helpful because our Z here, we can write it as an element of this algebra and just pick out the sort of field coefficients needed to express gamma, or we'll express z, and then therefore we can express gamma similarly. So z here, we might write as the sum of the Cij x to the I, y to the j. So this is just sitting here as an algebra, or as an element of that algebra. And what that tells us is that gamma, so being the reduced norm of z, is going to be in this subfield. So we just need the base field fp, and I'm going to need to adjoin omega 1 and beta, and then all of my Cij's. Okay, so that helps us find a subfield that our original symbol descends to, where we can understand the symbol length because we're going to have a field with finite p rank. So if we have A here, so we have this guy sitting in H3 p to the m of our original f, what we see is that descends to an A prime. So by restriction, it goes up p to the m f prime. And here f prime, let's see, that's going to be my fp, and I need to throw in all of these elements that gave me gamma. So that would be omega, except I'm not going to throw in only omega 1 now. I'm going to throw in all of the omega i's because I want to get my full H3 element, and this is in p to the m torsion. So I need my omega i's, I need beta, and I need the Cij's. And so here I have m elements, here I have 1 element, and here I have p squared elements. So that's where that number came from in the binomial in the theorem, because now f prime, so I guess I need to say a couple things. So f prime, this is going to have finite p rank bounded by this m plus 1 plus p squared. And our norm condition still holds down here in f prime. So this a prime still has exponent p to the m minus 1. Okay, so we can still bound the symbol length there. The other place where we can get our hands on the results is when the field has characteristic 2, because we have the language of quadratic forms. So f here is going to be a field of characteristic 2. Okay, now for any symbol A, that's an h n plus 1 to the m of f of exponent. So again, this is like the tenial example, but we're only stepping back 1 power of 2. So this has exponent 2 to the m minus 1. So its symbol length in h n plus 1 2 to the m minus 1 of f. This guy is at most m plus n minus 1 plus 2 to the n over 2. At least I guess we get a bound. And the proof is similar to the above. But this time, right, what do we have this time? So we have our A would be represented by something like omega with some B ends. And well, let's write our omega the same way we did above. Then the exponent of A equals 2 to the m minus 1. This now is going to imply that this symbol is trivial, omega 1 tensor B1 tensor Bn. Okay, so this we understand that that is going to be trivial, and that's going to be if and only if the Bn is going to be represented by a n-1 fold Pfister form. Okay. And then you can play the same games and find a subfield that the symbol descends to and maintains its exponent being 2 to the m-1. And that field is going to have the finite p rank, where the p rank is bounded by this numerator here. And then we can use, it's n, not 2. Oh, this here. Is that right, Em? Please send me a message. Adam, did I get that right now? It's choose n, not 2. Okay, yeah, sorry.
Yeah, because
typo.
of the inseparable.
Thanks. Yeah, so then it's the same game as above where you show that it descends. And we can control the symbol length using our previous theorem. All right, I think that's all I wanted to say.
Thank you. Are there any questions? So do you expect p to the n in place of 2 to the n in general in the last theorem?
For the symbol length bound,
Yeah.
I have no idea because I don't think we know how to control that at all. We kind of had to pick the situations where we could understand what it meant to have exponent 1 power smaller.
Are there any other questions?
Yes, I wanted to ask a question, but about the algebra part. You gave the result by Tignol 83. Can you go there? Is it, did I understood correctly? It says that cyclic algebra of p of degree p to the power t and exponent p to the power m is equivalent to p to the power t minus m cyclic algebras, right?
Yeah.
This, and do you know if this result is optimal for and like for a degree p square and exponent p? I am interested. Like for 2 and 3, I can see that this is optimal. But do you know if for bigger prime it is optimal or not, or any reference?
Yeah, that's a good question.
Because if I understood correctly, Karpenko's results give also examples examples of cyclic algebras which are intercomposable. So that would give optimal for also 3 p equal 3, because it says that you would have 3 symbol. But I would like to see if it is probably not from 5 on. It's like. From 2 to 5, for example, you have quite some difference.
I think that's a really good question. I don't know if anybody else knows. I mean, I certainly think that Karpenko's indecomposables are like the most generic way to write down the indecomposables, p-algebras. So my naive quick guess would that, they would, if this was optimal, you would see it there, but I don't really know. I don't know if anyone else wants to chime in. Yeah, that's a good question.
A result that I recently got to know, and it is quite I'm quite interested on that.
Yeah.
So I was thinking just wondered. Okay, thank you.
Mhm.
Are there any other questions?
And actually, one naive question. I don't know much about this cohomology groups, but when you give a symbol length for algebra, then there is the index which plays role in the symbol length, for example. But in your result that you gave an element in the cohomology group, then you have quite a generic bound for symbol length. There is no complexity such as index that change.
Yeah, I mean, we don't have a notion of index except in H2. So you're somehow only working with the torsion.
Well, you can still talk about splitting fields for some.
Yeah.
Exactly. Yes. Yes.
Uh-huh.
Yeah, absolutely.
And the GCM, of degree of splitting fields. Yeah.
Okay, so the elements, the degree of splitting field, even if it changes, it seems that the elements always have a same. You are obtaining generic bounds for any element, so the degree of splitting fields also would not play a role, maybe. But,
Yeah, I think that's right.
But okay, I
Yeah.
don't know much about cohomology, this cohomology group, so this was just a general question. Thank you.
Yeah, no, I appreciate it.
Well, this is a characteristic P phenomenon, presumably.
Yeah.
And in good characteristic, it will have to play a role.
Mhm.
It depends what you consider good characteristic.
Yeah, exactly.
Any other questions or comments? Well, if not, let's thank the speaker again.
All right.